we can keep track of our phone calls. Right? Let's do ammonia first. But the thing is, where's the KB chart here? Because when I look at that, I only see KAs listed there. And the thing is, because of the conjugate relationship, we don't need a KB chart. We can easily calculate it. Because it turns out that the KB for this, give me a minute. The KB for this is equal to KW over KA, where KA is for the conjugate. And so this would be KW over the KA for ammonium. Here. And so the conjugate relationship is like this. The KW is equal to KA times KB, where these are conjugates of each other. And so given one, we could figure out the other easily. We would have to know what KW is. And so if you write out the expressions, you'll see it cancels out. If you write out the Ka for, let's say, in this case, it would be the Ka for ammonium, and then write out the Kb for ammonia, and then cancel out all the terms, you're just left with hydronium times hydroxide, which is Kw. There's other relationships too. And the other relationships is that a lot of people don't like writing those because you know, you have to write it in scientific notation, which takes up space. And so what a lot of people prefer is to write it in terms of power functions, because if you write it in terms of power functions, you don't have to write the exponent, etc. And so what we're going to do is we're going to do this in terms of power functions. That is, the pKw is equal to the pKa plus the pKb, where, you know, pK, you know, the power is just the negative log of whatever you're looking at, base 10. And so P of, what should it be? X is equal to the negative log of X. Is that right? And so this is an alternate way of doing it. And so our book has it in both. You know, they have it in the Ka form and the pKa form. The pKa form is just more compact. So. All right, so next, what are we doing here? We're going to do some pH calculations. Well, there are different ways we could do the pH calculations. So let's take a look at, you know, Kw in detail. Kw is equal to the hydronium ion concentration times the hydroxide ion concentration. And so if we look at pKw, pKw is equal to the negative log of Kw, okay, which is going to equal the negative log of this whole thing, you know, basically. In other words, the pKw is going to equal the pH plus the pOH, the power function of the hydroxide ion concentration. And so, you know, there's a relationship between the pH and the pOH, and it's a seesaw relationship. And so as the pH increases, the pOH decreases, and vice versa. Or in other words, as the hydronium increases or decreases, the hydroxide will increase or decrease. Something like this. Although it's inverted because increasing hydronium is lower pH. There. And so these are the relationships that we use for bases. And so let's take a look at bases, like something like ammonia first. And so the example would be 0.100 molar ammonia. You know, what is the pH of this? Or what is the inventory? Oftentimes we're just interested in pH, not the complete inventory. We'll do both for this particular problem. And so for ammonia, you know, we know that Kb is pretty big. And so we're going to start off with that first. So ammonia plus water is going to yield ammonium plus hydroxide. And initially, we'll assume that no ammonias have collided with water, so this is 0.100 molar water. We ignore that. Water has to be present, of course. We just ignore minus X molar. plus X molar plus X molar. And so at equilibrium, we're going to have 0.100 minus X, X, and X. Now, Kb itself is just equal to the ammonium concentration times the hydroxide ion concentration divided by the ammonia concentration. Since it's a weak base, you know, most of it will stay as ammonia. Let's see what the percent hydrolysis is of this. So this is going to be x squared over 0.100 minus x. Then we'll just try the simplifying assumption. So this is going to be x squared over 0.100. This is going to equal 1.8 times 10 to the minus 5. Then that gives us an x of which would be the square root of 1.8 times 10 to the 10 minus 1, 10 plus 1, 10 minus 4. So square root of 1.8.
1.3 times 10 to the negative 1.3.
Okay, give me one more digit.
1.34.
34. Always carry one extra digit. You should get in the habit of that.
I'm still trying to count out my decimal.
Okay, so this is going to be equal to 0.100 minus, we'll get this in decimal form, 1, 2, 2 zeros, and a 1, 3, 4. And so this is going to be 0.09866. In other words, when you look at it, this is going to be 1.34% hydrolyzed. So just 1% hydrolyzed. And so most of the ammonia stays as ammonia. This is the reason why I don't want you guys on the metathesis reactions to write ammonium and hydroxide, because if you look at the amount of ammonium and hydroxide in the solution of ammonia, there's not much. You know, this is just 0.00134 molar, and this is going to be 0.00134 molar. But let's take a look at pH now. If we're thinking about pH, should I consider step 2, which would be Kw? I wouldn't, you know, because the most hydroxide I will get from water will be 10 to the minus, the most, 10 to the minus 7. Will having 10 to the minus 7 impact this at all? No, it's way too small. In fact, it's going to be less than 10 to the minus 7 because of the common ion effect. And so for pH, I would have just stopped here. Well, you stop here, and what I do in pH calculations is I would calculate the POH first. That is, take the negative log of this to get the POH. And then it would be pKw. pKw is equal to 14.00. Right. And so I just take the POH and subtract that from 14. And so that would give me what? Well, yeah, POH. Okay, and then the pH would be 11 point something. Okay, so pH is 11 point something. It's basic, and moderately basic, 100. But if we're interested in the inventory, we're going to continue on to step 2. So that was step 1, and then step 2, we look at the hydroxide ion contributors to this. So let's go ahead and do that. So for bases, we always look for the hydroxide contributors. So a hydroxide contributor would be water plus water, H2O liquid plus H2O liquid. This is going to give us hydronium and hydroxide. And so this would be the end of the line here for ammonia, ammonium, but the hydroxide we're going to carry down to step 2. And so we're going to assume that no water is hydrolyzed yet. And so we'll get 0 molar, and then over here we're going to have 0.00134 molar for the initial hydroxide. And so this is what we call the common ion type problem and a common ion effect. So plus X is going to be smaller than it normally is, and what it normally is 10 to the minus 7 molar. Right? And so why don't you finish this for me, and then I'll be right back. I gotta. So does somebody have the X? What did you get? Ten to the negative 12 you got? And you got 10 to the negative 11?
No, I got 12.
Okay.
The 0 somewhere.
All right. So the hydronium is going to be 7.46 times 10 to the negative 12. Okay, that would be the end for that. And then the hydroxide, will 10 to the negative 12 have any impact on this?
No.
No. Basically. And so this would be the inventory of the solution. We'd have ammonia concentration of 0.09866. And then the hydroxide would be the next most abundant, with a 0.031134. And the ammonium would be slightly be less than that, at 0.0134, and then hydronium's the lowest.
Do you want us to give an indicator that one's slightly higher and slightly lower when it's the same number? Or if we just put the number?
No, if you put the number, that's okay.
Excuse me, did you just give your simplifying assumption here?
Yes.
Yes.
The simplifying assumption is going to work here. The percentage is going to be very small. We use it for both calculations. All right. When the book does inventory, they often don't set up the ice table for this. They just usually set up the KW like this to calculate the other species. You know, we'll do it. We'll just do it the same way each time. All right, the next one would be 0.100 molar amide. For 0.100 molar amide, you know, amide is a strong base. Strong bases, this is just a one-way reaction. So amide is going to give us ammonia plus hydroxide. And so the initial is going to be 0.100 molar amide. Water, skip that. We're going to say no ions have been generated. The change here, you know, Kb is very large, so the change is going to be complete, 100%. So we're going to end up with 0 molar, 0.100 molar, 0.100 molar. Okay. Now, what's the next largest? Okay, this gets very tricky now, because what we do in base solutions is we look for the biggest K value, right? But we look for the biggest K value in base solutions, we're always looking for the hydroxide contributor. And so if you look at this, we have the strong base hydroxide, but you know what hydroxide plus water gives us? Hydroxide plus water gives us, if hydroxide hydrolyzes water, you know, hydroxide's a strong base, right? And so hydroxide should hydrolyze water completely, but if it hydrolyzes water completely, what does it form? It forms water and hydroxide. So is there any change there? And so for hydroxide, we don't, you know, hydroxide is there. But there's some other contributor. What's the other contributor of hydroxide here? Water. Water would be a contributor of hydroxide, but is there anything else that might contribute hydroxide to the solution?
Basic ammonia.
Ammonia. And so which one do you think will contribute more hydroxide? Ammonia or water?
Definitely ammonia.
Yeah, definitely ammonia. And so step 2 here is ammonia, right? Ammonia is going to be the next biggest contributor of hydroxide after amide. And so ammonia plus water, this is going to yield ammonium and hydroxide.
Why do you search for the next biggest contributor?
Because we do it stepwise, and stepwise we solve every single problem we solve the same way. We start off with the biggest K and work our way down. And so what we have to do is we have to be careful because we might just jump to water, but in this case there's an even bigger hydroxide contributor, which would have been ammonia.
Like ABC order.
Right, exactly. We just do it. And every, you know, whether it's polyprotic or monoprotic, we're just going to do it the same way, set it up the same way, and it should be okay. And so what we're going to do is we're going to drop this down to step 2, and drop this down to step 2. And so initial here, we're going to have 0.100 molar ammonia, 0.100 molar hydroxide, and we're going to assume no collisions have happened, so we have 0 molar ammonium. And then we'll allow it to equilibrate. So this is going to be, well, actually, which way is this going to go? Left or right? Yeah, there's only one way it can go. That is, we can only go up from 0. And so at equilibrium, we're going to have 0.100 minus x molar, x molar, 0.100 plus x molar. And so we look at Kb for this. This is going to be ammonium times the hydroxide, which would be x times 0.100 plus x. And this will be 0.100 minus x. Okay, and then, you know, I'm not even going to think about the rule of 100 or whatever else. I'm just going to do the simplifying assumption. If I do the simplifying assumption, then I get x is equal to Kb, and which is equal to 1.8 times 10 to the minus 5 from earlier. And so 1.8 times 10 to the minus 5, this is way less than a 5% change, right? And so we're good with that. All right, so go back up.
How do you get from here all the way to the answer?
Oh, how did I get from here to there?
Yeah.
Well, I just used a simplifying assumption. So this is x times 0.100 plus x. 0.100 plus x is just going to be 0.100. This is going to be over 0.100 minus x. Well, 0.100 minus x is just going to be 0.100. The 0.100s cancel. And that's how I got it. And so the ammonia here is going to be 0.100 minus x. So I need 4 zeros, 1, 2, 3, 4, and a 1, 8. And so this is going to give me 0.099 sub 982 molar. So I lose a little bit of the ammonia, and I'm going to generate some ammonium at 1.8 times 10 to the minus 5 molar. And then I'm going to generate some additional hydroxide at 0.100 plus 0.123418. And so this is going to be 0.100 sub 018 molar. what you see here is that the ammonia and the hydroxide did change a little bit, right? It was a 0.02% change or 0.018% change. Well, that could impact this, but does it? If the concentrations do change, is a strong base impacted by Le Chatelier's principle? That is, I can increase this. If I dump in a whole bunch of hydroxide in here, does the equilibrium shift left? No. No, and that's because Kb is very large. And so when you say that Kb is very large, we just assume it's 100% forward and it's only going to go one way. All right, what's the next biggest hydroxide contributor? Will be water. And so the next step, this would be a step 3 here, is Kw. And so what we're going to do is we're going to say, okay, this is going to be the end of the line for the ammonia. The ammonium is here, and then the hydroxide we're going to carry down to see how much additional hydroxide we're going to get from step 3. And so we're assuming that water has not hydrolyzed. The hydroxide here is going to be 0.100. So 0.018 molar. And so the change here is going to be plus X molar, plus X molar. And so at equilibrium, we're going to get X molar and then 0.100, so 0.018 plus X molar. And you got to remember the maximum X is going to be for base is going to be 10 to the minus 7 molar here because of the common ion effect. And so here, this is going to be X times 0.100, 0.018 plus X. The simplifying assumption should work pretty well here. So this is going to be X times 0.100, so 0.018. And then for X is equal to what? Kw, you should have memorized.
Negative 14.
Yeah, 1.0 times 10 to the negative 14. That's 2 sig figs. That's why pKw is 14.00. So if Kw is 1.0 times 10 to the minus 14, pKw is 14.00. That's 2 sig figs. 2 sig figs. And so what is X? Okay, 9.99 times 10 to the minus 14. It's a very small contribution. And so this is going to be 9.9 sub 9 times 10 to the minus 14 molar. You know, we didn't double check. I forgot to double check this one. No. You should double check it before moving on to the next step. Otherwise, we waste time. If this step was wrong, we'd have to fix the next step. So can somebody check this here to make sure? Okay, so we're good here. And so then over here, this this is 0.100 sub 0.018 plus 14 would be 13 zeros, right? So this comes out to 0.100 0.018 molar. All right, and so our inventory is going to be like that, the double boxed ones. This is what we expect to see in solution for this. But
wow.
Well, now I'm going to try to confuse you a little bit, maybe.
Uh-oh.
And that is, did I really factor in all the equilibria present? Because aren't I missing one? Because over here I had ammonia and I dealt with that, right? But here I also generated ammonium. If I have ammonium, isn't ammonium an acid? Yes. And so if ammonium is an acid, shouldn't I be doing Ka? Should I be doing Ka for ammonium?
Yes.
Yes, because it's an equilibrium that we should deal with. Because